This is functional patterns for the non-mathematician, and I'm Brian. Talk to me afterwards. Okay, so this talk is kind of an experiment. I'm just going to blast through a ton of slides, all these different patterns and abstractions. These are some of the ways you can use these abstractions. You know, pattern this, pattern that, and then we'll go play with it in code. So you're not really supposed to see exactly everything about what I'm going to show you. You're just supposed to kind of get a feel for what to use where, and then if you want to go try it, you'll kind of know what abstraction to look up because you'll have an idea. So we'll see if the experiment works. I don't know. Here we go. All right, first we got to get in the mindset. We have this add function that I wrote, and I thought this up. And what it's going to do is going to take two numbers and it's going to combine them into one number. But you probably already knew that because it's add. It's from math. It's bigger than programming or my personal, ideas about what should happen. We know a lot more about that too. It's got associativity, and we even know how multiplication works with it. It distributes over it. So you have this wealth of knowledge just because we chose to use this add function. And it's also polymorphic. Now in JavaScript, it's just a number, but it works on fixed nums and big nums and integers. So it's a polymorphic function as well. Now, by contrast, we have this increaser object, right? And you can argue that it's plain English. You can read it, and you can see exactly what's happening. But you have to go look up documentation. I would have had to write documentation originally. And you don't really get all those free features we had if I just used add in the first place. So it's nothing wrong with that, but what we're after today are polymorphic composable interfaces that have these properties or laws. Same difference. Okay, here we go. Does anybody raise your hand if you know what currying is? Okay, there's a good amount. I'm just going to fly through this real quick so you can see for the people who don't know. So we have this array of names, and I have a function called take. And I could say maybe take 3 names, right? And that'll give me the first 3 names. Well, take is a curried function. That means I can give it less arguments than it expects. So I can give it 2. And it doesn't just run with the array as null. It'll just give me a function back waiting for the rest of its arguments. So I can actually define something like first just by giving it part of its arguments. And now I can get the first out of the x's. Is everybody able to read that okay? Is that too low on the screen? Either way, so you can give a function less arguments than it expects. It returns a new function back, waiting for the rest of its arguments. That's what currying is. Okay, moving on. Composition, that's really easy. It's just taking a few functions, gluing them together, and returning a new function. So if I call this reverse cap function with hello, we get ole. Let's see how that works. So hello is going to go into reverse. It's going to get reversed. And then it's going to go into capitalize it, and that's our result. So it goes right to left, piping the data through each function as it goes. So that's composition. Okay, the cool thing about composition is it's associative. It comes from category theory. So we know that we can group it. We can do any inner compose. It doesn't matter how it's grouped. So we could just write as many functions as we want. We don't actually have to bother writing those inner composes. What this means for us is we can actually extract any inner compose into a new function. So that's really neat. It makes Martin Fowler's extract method refactoring dead simple. So there's compose. We'll be using some of that. And we can write full programs with it. We could say this program here just gets some users from the database and actually renders a table with their names. But it's kind of a perfect world. You're just piping data through all these functions, and we're going to hit these little hairy bits that you have to deal with in programming, like null checks and asynchronous values and all those things. So that's what I'm going to show you patterns to help you with here in a few seconds. And we're just going to strap in, hold on tight. We're going to see a ton of patterns and a bunch of ways to solve that, but in this context of this functional way to write JavaScript. Okay, here we go. First, pattern. All right, so here's some getters and setters. And you might find yourself writing these generic getters and setters. Well, you can use a lens for that. Here's just a few functions that lenses export. Let's see how they work. So we have this user object, and we make a lens for name. So we have l.name, and you can view the name, or you can set the name, or run functions over it. But notice, if we set or run functions over the name part of that user object, we get a full user back. That's because it's making a copy of that user with a new altered value. So it's being immutable, and it's letting us just reference that one little part. Another cool part about lenses is that you can compose them together. So if we look at this first name char part, we have this composed of a name lens with a first lens with this index 1 lens. It's that _1 thing. That'll get the first part of the string. So we're actually peering into this user and grabbing that D in Doris, and we can actually run 2 uppercase over it, which is pretty sick. That's why it's called a lens, is because you can peer into this data structure. But what we've demonstrated was that it's composable and it's polymorphic. It composes with other lenses that work on different data types. So we've got our composable interfaces that's polymorphic. What about laws? We've got laws. I'm not going to go too into the laws. They're as simple as, if you set it twice, the last set wins. You kind of have to squint and make real examples. I'm just going to show you that there are laws throughout. OK, there's lenses in 10 seconds. So here's another pattern. We've got null checks. So we're going to run our function if it's there. And you can do that in a functional way by dropping our value inside a maybe and fmapping our function over it. We're going to see fmap a whole bunch. So let's look at what that looks like. So fmap takes a function and a mappable, and we're going to call .map on the mappable with a function. It's pretty easy. So how does it work? We've got our maybe object with hi in it. And when we fmap this function over it, x becomes maybe's property. It becomes the string hi. And then it'll uppercase it and return us a maybe with hi in it. OK? So x becomes the string hi here. And here, since there's no thing in the maybe, it just doesn't run it. We're in fact asking maybe to map this function over its property. And maybe's like, no, I'm not going to do it. It's not there. I won't run it. But we don't get a big null.toUppercase explosion in our face. It just returns maybe null. So maybe it's just a constructor function, but it's a function. So we can compose that constructor. And we can partially apply fmap because it's curried. All right. So it's got some laws. We've got identity, and we've got composition. I'm just now realizing this is like the last talk of the day, right? Or yeah, probably. And you guys are probably fried already. So I'm sorry. I'm sorry about showing you this. But this is a cool law. It's composition. So we're going to go through another pattern. There's going to be like 5 or 6 more, and then we'll go play with it and have some fun. OK. Here's error handling. So this is just one way to use this abstraction. But let's say we don't have, if we have a null, we're going to throw an error. So we can do that functionally by saying, or in a more categorical sense, by saying, hey, I'm going to use an either with some error and x, and we're going to fmap over that, just like a maybe. So here, we have to learn how it kind of works to understand it a little bit more. So either is a superclass that has 2 subclasses. It's left and it's right. So it takes these 2 arguments, and if its second argument is there, it returns us a right with that value in it. But if it's not there, it returns us a left. Can you guys see, is that too dark or light of a gray? Can anybody see? Thumbs up? All right, cool. So yeah, so it's going to return us a right or a left based on if it gets its right argument or not. Well, why does that matter? Well, if our fmap is running on a right, x becomes 2, and we're going to add 2 to 1, and we get a right of 3 back. But if we get a left, it's not going to run it at all, just like maybe. It just doesn't do it. So that's pretty neat, except we get our error message embedded in there. So that's helpful. And if we're going to put it in a compose, what's going to happen is the value will go into the either and complete that call, which will return a right or left. And then it'll run into the fmap over the right or left there with that function. All right, another pattern. Future values. OK, so you want to do something with the result of calling another asynchronous function. This happens all the time in JavaScript. We've already seen talk about this, but there's promises for that. So it's the same pattern as we've been seeing over and over again. It's like a pattern within patterns now, getting crazy. So x goes in our promise, and we just fmap over it. In practice, it's a little bit different. We have to actually make a promise, and then we're going to fmap our function over that promise. But x will become the value when the promise is resolved, and it returns us a promise for a composition. And then we resolve it, and there it is. It reverses it, and it logs it. So I haven't been going over these fmap laws because we showed you them a few slides back, but it holds for all these different things. And all these things are called functors. So that's just something that implements map and obeys those laws we saw earlier. And it's a really useful pattern. It's what a lot of other things are built on top of. So promise, maybe, either. These are just some of many, 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 many functors out there. All right, let's move on and away from them and do a new pattern. And it was pointed out to me that some of these aren't actually patterns, but it doesn't matter. OK, so nesting. Let's say you've got all these values, and they're just going to keep nesting with these patterns over and over and over again. We've got null checks inside of null checks inside of null checks. Or let's say you have callbacks inside of callbacks inside of callbacks. Or another name for that is a node app. If you actually put this little magic M join in there, it'll actually kind of take that nesting and kind of join it together. That's a pretty cool thing to do. Let's see what happens. It's a longer example here, but so in our greet function, what we're going to do is first we'll get the field, which does a query selector, and it may or may not find this input or whatever we're looking for. So it's going to put it inside a maybe. And then after it does that, we're going to fmap over that maybe to get the value of the field. But it might not have a value, so then it puts that in a maybe. And now we have to fmap concat, which is kind of clunky. On one hand, it's kind of cool, because you can see that there are two obvious null checks in here. We have this kind of type safety that shows us, we've got two possible failures going on. But on the other hand, it's kind of clunky. And if we just drop a little M join in at the part right where it gets nested, that's where it's just going to join those two maybes together, kind of flatten them, and then we could just deal with one maybe from here on. So that's a cool thing to know about, and we'll use it in a minute. All right. So you could also see, this is a monad, by the way. So you can fmap our function, and then we can join it, and fmap another function and join it. And this could be seen as a kind of composition in itself. So let's define mcompose as the composition of f and g, just so these laws look pretty. And then we're going to ignore it. So associativity and left and right identity there. OK, another pattern. I think this is like last one or two patterns. I don't know. We'll figure it out. OK, so you've got two different values that may or may not be null. And we want to run our function on it. Or you've got two different asynchronous calls, two different future values, and we want to run our function when both of those values are finished. And this is a pain in the butt. I don't know how many people have tried to do this, but you got to wait for two things to resolve, and then you got to call your function with it. There's nice promise libraries for that, but the way we're going to solve that functionally is with lift A2. You guys might have seen this around the block. It's really just fmap for a function with more than one argument. So we're going to run our function f on this a of x and a of y. Well, this a can be replaced with a maybe or an either or a promise. And if f takes more than two arguments, let's say it takes three arguments, you've got lift a3. And you got lift a4, 5, all the way up to like 10 or something. If you have to do more than that, you shouldn't be programming, just so it doesn't matter. OK, so we've got lift a2 with add. How does this work? What's going to happen is add is just going to be applied to both of these maybes, and it returns a new maybe. Easy as that. It's just fmap with multiple arguments. But if any of those maybes are null, it just won't run it. So that's a cool pattern. You can say if anything is null here, we're not going to do it. We can do the same thing with promises, or any other functor for that matter. But this is kind of a half-baked example. But really what I wanted to show you is that make collage here will be called when both promises, both our tweets and our photos, is resolved. And it has to be curried. Anytime you're using lift a2 or lift a3, etc., the function going in needs to be a curried function. OK. And there are laws, yada, yada, yada. OK, here's a non-pattern. OK, I'm running out of time. I want more time to play with code, so I'm just going to fly through this really quick. So you've got a reduce. It's got a plus and a 0. got another reduce. It's got a multiplication and a 1. Let's get a product. We got another reduce. We've got an or and a false. We got another one and true. We're seeing a pattern here. We've got greater than. It's a little different, but basically start with 0 and keep the highest one. All right. All these reduces are really pointing to one thing, and this is this mconcat function of a monoid. What we have here is a monoid. And you can actually embed that reduce into the type. So sum knows it needs to start with 0 and add. So we can pretty much fold down a list of sums or products, or grab the max, or use any, or all, and there's more than that. You can do it on strings. And you're mainly going to see it in a composition with, we're going to first take this list of stuff, put it inside our monoid type so it knows what to do, and then it's just going to mconcat it. Okay, so we've got some laws for that too. And the benefit here, if you've kind of been like, why would I do that, is because we've got these generic, functions just like add that have properties and laws, and they're polymorphic, and they've got this intuition on how to use them. So you can kind of swap these types out, and you know all this stuff about your program. Okay, I'm not going to go over arrows. I'm just going to. There's the end of my slide, and we're going to play with some codes. But if you want to play with the code yourself, it's all at this patterns talk repository. So go rip it apart, make some pull requests, have fun. And I'm Dr. Boolean on Twitter if you want to yell at me. Okay, let's have some fun here. So here's the code. So we have a comment here, and if let's look at this program. We're going to pluck the body of this comment, mark it down, then show it on the screen. And we're just going to log here. You could imagine inner HTML or render template or API call or whatever. But so we're just going to go through and mark it down. And if we run it, boom, it worked great. We've got our markdown body here. Well, so this is a patterns talk. So we have a fictional boss from all those patterns books, and he's like, oh, you're going to lose your job unless you show the whole comment on the screen for me by the end of the day. So just look at my watch. I looked at the other hand. Anyway, so we have to actually show this full comment on the screen. And the problem is we pluck the body and we lose the rest of the comment immediately. Then we mark down the body, and then we try to show it on the screen, but we lost the comment. Well, you can do this kind of by just mutating the comment. We want to mark down its body. We want to do like a setter. Oh, and also we want to turn viewed to true, just for good measure, because they're actually viewing it. So what we can do here is, does anybody know what we might want to use for like a setter, where we get a copy? Yes, that's it. Thank you. Please shout it out. I just wanted to see if the experiment worked. If you don't know, it's okay. But, all right, so we're going to make lenses, and we'll make one for body, and we'll make one for viewed. And now we've got these two references. So what we can do is say, well, we don't need to pluck the body anymore. We're just going to say, over our body, we're going to mark it down. And then over the viewed, we're just going to turn it to true. Boom, let's see if that works. Yes, it worked! I was scared there. So yeah, it gave us our whole comment, and it updated the body, marked it down, turned viewed to true. So lenses are really useful for that kind of thing. And they actually work with functors too. I didn't mention this before, but you can actually look into promises and futures values and null checks and whatever. So lenses are crazy powerful. They're actually built on functors. Speaking of functors, so we have the hottest app in the App Store, and it's a word counter. So it's going to grab the amount of words, or match the words, and then grab the length. And if we run that, let's clear the screen. So it tells us 4, and we've got 4 words here. Well, we've been getting all these complaints, right, from all these people that are like, well, your program isn't doing anything for me. It just blows up in my face. It says, can't read property length of null. What's happening here is we couldn't match any words, so we get a null right there, and we try to pluck the length of null. We can't read property length of null. Does anybody know what you might want to do here? All right, I'll tell you. It's maybe. All right, so we're going to put a maybe right there, and then we're going to call fmap right here. And that's all we have to do, because we can't pluck the length of a maybe. We have to fmap to pluck the length. So let's see if this works. Well, for one, we want to make sure it doesn't blow up anymore. Doesn't blow up. Great. We get a maybe of null. But if we add some words, we get a maybe of 2. Great. What's awesome about that is we've kind of marked the beast. We've said, hey, this thing might not return something. So let's do a quick refactor here using some of those properties that that is motivating us here. So I'm going to actually use associativity with this compose and pull out a subcompose. I'll call this match words or get words. All right. And we put a maybe right there for us so we can say, hey, anytime you match words, you may or may not get words back. So we're going to put it right there so you have to deal with it. That's a little bit of type safety. It's pretty nice. And then let's just go ahead and say I'm going to add or concat like the count is. All right. And we want to, give our version 2 program, a little extra pizzazz here. So we'll say, grab the length, but we can't actually tell it concat a string with that. We have to fmap, right? Because we're getting a maybe 2. What we want to do is fmap so it says the length is 2 inside the maybe. If we run that, it works great. We say that maybe the count is 2. Now, it's going off the screen, huh? Let's do it like this. All right. Forward comments, anyone? All right. So what's cool about this is we know from a property from the functors with fmap that if I see an fmap and an fmap in a row, I can actually pull that into one fmap and compose the inner function. So we're actually using these things we're learning from the properties to make our program a little bit better. Back to the original way. All right. So let's call that show count. And we'll just say, you know what, instead of compose fmap, we'll fmap compose. And actually, one thing that might be a little bit nicer is that this show count is expecting a functor, but it really should just work on any string, right, or anything with a length. So let's just call this inline. So we'll just fmap show count. Great. And there's our hot new program, handles null checks, shows the count. Oh, I got a syntax error. There we go. There it is. Awesome. Okay. So now our boss comes by and says, listen, guys, I don't know what you think you were doing, but like when you don't get anything, it just says maybe null. What the hell is that? Nobody knows what's going on. So we need to say something to the user to explain, what they need to do. So we actually have to convey an error message. Does anybody know what we could use to convey an error message across? Just shout it out if you know. I'll give you a hint. It starts with an E. Yes, thank you. All right, so we'll just say either. You need some words. There we go. And that's it. So now if we run it, it gives us a left of you need some words. Or if we actually have words, blah. There it is. We get it right, and the count is 1. So that's pretty neat. We're doing our pure error checking right here. So I've got a few minutes left, and I've got several examples. Do you guys want to look at monads or monoids or applicatives? All right, monads it is. Everybody loves monads, right? All right, cool. All right, so now let's back to our normal word counter program here with the maybe. So this is the biggest challenge of our life here. We have a read file. We got to read a file from the file system, and we're actually going to grab the word count from that. But we're going to go one step further. We're going to ask the user what file they want. So we're going to ask the user what the file is. We're going to read the file, and then we're going to do our word count. And I've just kind of written the type. Those of you who are familiar with the kind of Haskell type system, it's going to take a string for read file and return us a promise of a string, which is that file contents. Same thing with ask user. It's going to ask what to ask is the string, and then it's going to return us a promise of what they actually typed. So we got to make our program here. And it's going to be the composition of asking the user what they want, reading the file, and showing the word count. Great. And let's say that's our result is running our program with what file? There we go. So the interesting thing here is this isn't going to work because these are all asynchronous, right? So what we have to do is actually, since ask user returns a promise, we're going to fmap over that promise to read the file. But then read file returns another promise, and it's going to put a promise inside a promise. It's that nesting thing that we had to deal with. So now we have to do an fmap, show word count. And this will work, I hope. Let's try it out. What am I on, 6? Oh, boom, show length is not defined. Where's that? Show count. There it is. What file? We'll give it my Gadsby text. And what did I do wrong here? Ask the user to get the file, show the word count. All right, well, this isn't working right now. Let's figure this out. Let's do a different one. I can make this a little bit nicer. All right, let's say we want to get the words inside, do like 2 null checks instead, right? So what we're going to do is get the words, and then let's call our program with text. Let's say we've got a text of some words, and instead of actually putting it right into the program, we're going to pluck the text property. So here we're going to grab the text, and then we have to actually get the words from that, and then we're going to show the count on that. Well, what if text isn't there? What if it's misspelled? What if it's test? What we're going to have to do is put that inside a maybe, just in case it's not there. So we're going to get the text, put it in a maybe, get the words, which comes back in a maybe, and then we have to fmap, show count. Let's try that out. Let's see. So log this thing. And prog text words. Oh, there's our prog. And another problem here. Don't worry, guys. We got this. We just got to fmap. There we go. Okay, so we got a maybe null because it's misspelled as test. But if we do text, we get the maybe, right? Just like we talked about earlier. What's cool about this is all we have to do is drop an mjoin right here. And then we don't have to maybe or fmap anymore. It just flattens those two things together, and we could just run it, and it's a maybe. Nice. And that's all monads are. You don't really have to think about this situation. You're just nesting these objects inside of objects inside of objects, and you have to join them at some point because you're like, this is ridiculous. I've got these Russian doll kind of object nesting thing going on. And that's all the mjoin does. We also have flat map or chain or mbind. It's all the same thing, which is just, the definition is just fmap then mjoin. So we could actually flat map that. And the way to look at this is saying like, we're building up new functions based on other functions, and we have this kind of algebra here of generic property-based functions, so we can actually rely on all these other functions that have been built using these constructs. All right, so I got a minute left. I don't know if I should go into another example or try to fix that awesome ask user part. It's going to haunt me forever unless I fix that. Let me just take some questions. Does anybody have any questions? What's up?
What's point-free fantasy?
Oh man, that's a good question. All right, so there's this Fantasyland JS. I don't know if you're familiar. Fantasyland JS is just a more like Scala-based, functional mentality in JavaScript. And basically what we're doing is taking the Fantasyland spec and using it with the kind of point-free, compose, curried functions that are more Haskell-based. So it's just translating the spec into a Haskell-style spec. So, anybody else?
What library were you using?
Right here? You can just go to my GitHub. There's a mess of requires. It doesn't even matter. We've got maybe and promise here. I should probably be using Q. It looks like I'm about out of time. But yeah, go to the GitHub repo here and go play around with it. And meanwhile, I'll try to fix that ask user thing. So any other quick questions before they kick me off of here? All right. Thank you guys so much.